For attending my talk on metatarsophalangeal joint mechanics, longitudinal bending stiffness, and how that relationship may change across running speeds. As a disclaimer, I am an employee of Brooks Sports. This research is from my dissertation at the University of Oregon with Dr. Michael Hahn and does not represent anything currently being done by Brooks Sports Run Research Lab. For background about the MTP joint, when you increase longitudinal bending stiffness, what is often observed is a reduction in dorsiflexion range of motion or peak dorsiflexion, an increase in moment, and a decrease in negative work. We also know that the MTPJ changes mechanical behavior with running speed, notably an increase in range of motion and an increase in moment as we run faster. However, one limitation to a lot of longitudinal bending stiffness research is that it's all been done at one single running speed. And so the question we had is, does the response of MTPJ mechanics to footwear of varying longitudinal bending stiffness speed dependent due to how those mechanics change as we run faster? We had three main hypotheses for the study. One was that MTPJ dorsiflexion and MTPJ negative work will have a speed dependent response. We think this will occur because as we run faster, that larger moment about the MTPJ will perhaps have better capacity to bend footwear, and we won't see a systematic reduction in dorsiflexion with a stiff plate at faster running speeds. However, we do think that MTPJ moments will not have a speed-dependent response. We think that at each speed we will just see a lever effect of having that stiff plate in there and increasing the moment. For the study, we recruited 10 competitive male distance runners. They ran on an instrumented treadmill at three speeds, 14, 17, and 20 kilometers per hour. At each speed, they ran in three different stiffness footwear. Shoes were modified with a nylon 11 plates to increase stiffness. These plates were 3D printed to fit the footbed of the shoe, and each of them were 3 millimeters thick. The normal shoe was just the normal off-the-wall shoe, a Nike Epic React. The stiff shoe had one 3 millimeter plate, and the very stiff shoe had two 3 millimeter plates. For data analysis, we used a two-segment foot model with markers on the forefoot and rear foot, or the calcaneus. For kinetic estimations, we used just standard inverse dynamics at the sliding MTPJ joint center, and then joint energetics, the power about that MTP joint was calculated respectively with this equation. For statistical analyses, we used a repeated measures ANOVA at each speed with the respective Bonferroni adjustments to address the question of is the response speed dependent. That's where we looked at the statistics and if there's a different main effect from what the p-value is telling us, or if the post hoc comparisons were different across different speeds, then we assumed that we were then seeing a speed dependent response. Looking at the variables that we hypothesized would be speed dependent, starting with MTPJ dorsiflexion. Over here on the right, you see the three speeds, 14, 17, 20 kilometers per hour, top to bottom. Again, the orange being the normal shoe, the stiff with one plate being the green, and the purple being the very stiff with two plates. What we see at each speed is a systematic reduction in dorsiflexion, and so we can conclude from this that there is no speed-dependent response as we run faster, and that increased longitudinal bending stiffness reduced MTPJ dorsiflexion at all running speeds. Again, this was contrary to our hypothesis. We thought that the greater moment about the joint at the faster running speeds would overcome having a stiff plate in the shoe. From this, we were kind of thinking that perhaps the MTPJ is not the primary mechanism to overcome greater longitudinal bending stiffness. Two things we could think of here. One is just related to intrinsic foot muscle strength. The moment that the intrinsic foot muscles are able to generate about the MTPJ is much smaller than the external moment about the joint that we see during stance. Secondly, it could just be the path of least resistance, or when you have a stiff plate in there, it's going to require increased muscle activity and increased moment to overcome that plate. So it could just be that, the body is kind of reorganizing how it runs, thinking about the habitual motion path, and it's just not advantageous to really work against the plate. It's just going to not dorsiflex as much due to the different environment that the foot is now working in. When we look at then the MTPJ power curve, thinking about that negative work hypothesis, similar results bleeding over just from that change in dorsiflexion and then the subsequent angular velocity of the segments about the MTPJ joint. And again, so no speed-dependent response here as well. Of course, integrating the negative portion of this curve, there's less negative work with greater longitudinal bending stiffness, again tied to that kinematic root. So you can see here the normal shoe is in that negative phase for longer and at kind of a larger magnitude throughout most of the stance as well. Looking then into the kinetics, which we hypothesized would not be speed dependent, this did hold up. We see no effect across the different speeds. Additionally, we also saw no effect of longitudinal bending stiffness. We think this is happening because of the non-rear foot strike gait of 9 out of 10 of our runners that we identified when we post hoc analyzed their foot strike pattern. It could just be different in how that center of pressure is really catching velocity and translating across the footbed. This could also be related just to the comfort filter. These plates were top loaded. They were placed just underneath the sock liner. They're not in the middle of the midsole where someone has 10 millimeters of foam plus another 4 millimeters of strobe sock liner. So it could just be uncomfortable for someone to really push into and lever across a plate that's going to be a little bit harsh underneath that footbed, especially under the large forces at faster running speeds. Interestingly, when we then plotted the passive torque contribution from the shoes at each speed, this is an exemplar graph. All figures look the same at each speed. The very stiff shoe did contribute the most amount of passive moment in a systematic order, going stiff then to normal, despite not bending as much. So interesting when finding here. This does also relate, though, to an interesting point where with this data set, we identified that the very stiff shoe, people had the worst running economy, even though the shoe is theoretically here doing the most for them by contributing the most amount of moment. What this all got us thinking to is around where are sources of error within this study, and where could we potentially have made better conclusions if we were able to eliminate those sources of error. The first is around imaging. Within this study, we assumed that the foot and shoe were one unit. In this case, we used the MTPJ ankle and the footwear bending stiffness to estimate that moment contribution from the shoe. However, we know something that commonly happens with shoes is heel slip. So theoretically, there is a different MTPJ angle between the foot and the shoe. However, we did not go about quantifying this because we were just using the markers on the shoe for this. Increased X-ray imaging could help identify this. This has been done for cutting movements, but not so much with running gait, where you don't have a finite location on the treadmill where you're able to get that foot strike down and analyzed. So within the use of just kind of standard markers, this is a limitation. Regarding then the second area we thought about was mechanical testing. We know that all these materials exhibit a viscoelastic behavior, and if the test speed of the mechanical testing does not equal that of the dorsiflexion velocity, then due to that viscoelastic behavior, it could actually be different stiffness of those shoe that is happening. Secondly, the midsole of a shoe is commonly not compressed during testing. So you can think that when you compress a midsole through the vertical ground reaction force, it's going to become stiffer. However, during forefoot bending stiffness test, the midsole is often unloaded, so we are not really quantifying the effect of, say, a plate and a compressed midsole. It's often just a plate. And then last point I wanted to address around forefoot bending stiffness tests is there's no common method to do this. And so it makes it hard to translate findings across studies and then really understand what are the sources of error when we try to extrapolate further to understand, what is this shoe and its stiffness actually doing during gait, as opposed to just quantifying stiffness of shoes and calling them normal, stiff, or very stiff. So altogether, really hypothesizing here and thinking about what are areas within data collection methodologies that we really could start eliminating error that we see within kind of the use of conventional 3D motion analysis. So altogether, we saw no effect of speed on longitudinal bending stiffness by metatarsophalangeal joint interaction, and then we identified some areas for perhaps better translation of mechanical testing results to help eliminate error during these types of data collections. Thank you to the Bowerman Sports Science Clinic, notably Dr. Michael Hahn, for all his help and support during my dissertation from which this work came from. And if you're interested, we have published this research. The paper also contains joint level mechanics of the ankle, knee, and hip. Thank you for attending.